All right, good afternoon. Today we are going to be doing the alternating series test, but we did have a question that I posed at the end of the comparison test. Okay, so the question that I posed at the end of the comparison test. Oh, I did not pose that question. All right, so here it is. All right, so for this comparison test, limit comparison test, we need to determine whether this series converges or diverges. And we're using the limit comparison test for this. So our AN is the series that we have. AN is 1/2 to the n minus 1. So now, as I said before, I want to do what I call like scratch work. And over here, I need to see what 1/2 to the n minus 1 looks like as n goes to infinity. Now I can see, I did the same thing in the other class. Okay. So as I can see that as n gets very, 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 very large, 2 to the n dominates, becomes extremely large, goes to infinity. The minus 1 is there. So this looks like 1/2 to the n. So that is what I'm going to call my Bn. So Bn is going to be the function that this somewhat looks like in the infinite world. And so now I have An and I have Bn. So here's An. And here is Bn. Okay, so I now need to compute the limit as n approaches infinity divided by Bn. When I take An, which is a fraction, and divide by Bn, which is also a fraction, I'm going to divide by the reciprocal. So I'm going to get the limit as n approaches infinity. Bn is going to give me 2 to the n in the numerator. And in the denominator, I am still going to get 2 to the n minus 1. So I need to compute that limit. Okay, how do I compute that limit? Somebody want to give me some help, please? Looking at what happens as n gets very, 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 very large.
Can we use L'Hopital's rule?
Okay, so this does indeed go to infinity over infinity. So I can use L'Hopital's rule.
Could we take the derivative of the top and the bottom?
Yes. Okay, so now this takes us way back to taking derivatives of exponential functions when the base is not. How do you take the derivative? How do you take the derivative of 2 to the n? What do you get?
Is it, wouldn't it be like the n goes to the front and then it's the exponent minus 1 or plus 1?
Okay, I can only do that if the base is x. So what we're trying to do is we're trying to take the derivative of something that looks like 2 to the x. Okay, you're thinking of taking the derivative of x to the n. Here,
Okay.
yeah, so I'm not talking about the second one. I'm talking about the first one. So how do you take the derivative of 2 to the x? What is f prime? How do you take the derivative of e to the x?
It's just e to the x.
Good. Now, when the base is not e, it's
Oh,
still,
wait, I think I know.
what is it?
Um, is it just gonna be 2 to the x and then you have to have the natural log of 2?
I am so pleased with you. Okay, so this becomes 2 to the n, natural log of 2. And then the derivative also becomes 2 to the n, natural log of 2. So that's just the limit as n approaches infinity of 1, and that is equal to 1, which is greater than 0. Okay, so this right here is my L. Remember, for the limit comparison test and the direct comparison test, I need a number L. I got it. I'm happy with it. It works. So now these series both converge or both diverge. So now I need to examine this series to determine if it converges or not. If it converges, the original series converges. If it diverges, the original series diverges. Okay, I'll give you a hint. I'm going to rewrite this. So now what does that series look like?
Is it a P series? No.
It's not a P series.
Oh, wait.
I can't see you, but I can see your brain working.
Geometric.
It's a geometric series.
I was gonna say that.
Okay, so this is a geometric series. And it's not quite the one we're used to looking at. We're used to looking at the summation n equals 1 to infinity of 1/2 to the n minus 1, right? That's what we're used to looking at. So this is just missing the first term. So the first term of the series with the n is 1/2. The first term with the series in red with the n minus 1 is 1. So this is missing the first term. So it's missing the sum minus 1. Okay, so now what do you know about this series? This is also a geometric series. It's the same series minus 1. What do you know about the series? Does it converge or diverge?
Converges.
It converges. Why?
Because it's basically where you have n minus 1 and the exponent.
Now,
Wait, hold up. Wait.
there's a real rule for this. Geometric series converges under one condition.
Is it when it's I'm not sure. I'm not gonna guess because I don't want to be wrong.
Okay,
I'm not sure.
I can tell you're thinking this converges because the absolute value of r, which is the absolute value of 1/2, is less than 1.
Okay.
You got it?
Yeah.
Okay. So this series converges, which means this series converges. And this series converges, which means this series converges. All right, so all of that now implies that this series converges. Right? So by geometric series, summation n equal 1 to infinity of 1 over 2 to the n converges. But now that series converges, and remember they both converged or both diverged. So by the limit comparison test, my original series, summation n equals 1 to infinity of 1 over 2 to the n minus 1 also converges. Okay, so that is the last that we wanted to do of the limit comparison test and the direct comparison test. Questions? Comments? Okay. So today we are going to do the alternating series test. In this section, we will use the alternating series test to test an alternating series for convergence. We will estimate the sum of an alternating series, and we will explain the meaning of absolute convergence and conditional convergence. Okay, so the first thing I want to do is look at the series that we've already done. Okay, so put your thinking caps on because I'm going to ask a couple of questions. All right, which series can you actually find the sum if the series converges? Hello? Which series can you actually find the whole sum, S, if the series converges? Anyone? What's that? The geometric series? Yes. Anyone else? Thank you, Devin. Anyone else?
It's not more than one series, is it?
It certainly is. It's two of them.
Telescoping.
Telescoping series. Okay, thank you very much. So yes, the telescoping series and the geometric series, we can actually find what the sum is if the series converges. Okay, what series is it that the exponent of the denominator determines convergence?
P series.
The P series. And when is it convergent?
It's greater than 1.
Okay, P has to be greater than 1. Awesome. What series is it, series test, do I use if I want to take my series and bound it by a series that converges, so it's less than one that converges, or it's greater than a series that diverges? Which
Can you repeat
series,
that one more time?
which series is it that I want to take my series and make it smaller than a series that converges, or make it larger than a series that diverges?
Yeah.
Direct comparison.
That is a direct comparison test. Thank you, Prentice. Okay, which series cannot tell me that the series, which series test cannot tell me that the series converges?
Is it the nth term?
The nth term test of divergence cannot tell me at all if a series converges, only tells me if a series diverges. Which series test can be used on the sum of terms that are in fractional form or can be put in a partial fraction form?
Telescoping.
Telescoping series, awesome. Which series test can I look at and create a function? And then if the integral of that function converges, then the series converges. And if the integral of that function diverges, the series diverges.
Integral test?
That's the integral test. Okay, which series test diverges if R is greater than or equal to 1?
Is it the P series? No.
Okay,
Geometric?
it's the geometric. Thank you, Devin. Rodney, the P series has a P greater than 1.
Okay.
Geometric series has a R, absolute value of R is less than 1. Okay. All right. And the only other test I didn't ask you a question about, we just did. If I find another series and look at the limit of the ratio of the two series and compare them, obviously that is the limit comparison test. Okay, so I think you guys are getting it. I'm happy to see that. I'm going to pause real quick, take attendance, and then we're going to see if I can do the alternating series test. Okay, so today we're going to look at an alternating series. And this is what the form of an alternating series is. So for the alternating series test, what we're going to do is we're looking at series whose terms alternate between positive and negative. So as you see, I have the first term. If you put in n equals 1, I get 1. If I put in n equals 2, I get a half, but I get -1 to the 1 plus 1. So that gives me a positive, a negative. Oh, I'm sorry. When I put in 2, I get 2 plus 1. So that's -1 cubed. So that is negative. When I put in 3, I get a 3 in the denominator, but I get -1 to the 3 plus 1. So that's to the 4th. So that's positive. So as you can see, these terms go back and forth, positive, negative, positive, negative, positive, negative, positive, negative, positive, continue on. Okay, so that makes this an alternating series. And the next one, as you can see, is also an alternating series. All right, it looks like 1 over 2 to the n, or it kind of looks like a geometric series, but it's got a -1 to the n plus 1 in it. Okay, it could actually be -1 to the -1. Okay, so sometimes you will see to the -1 to the n plus 1, you will see -1 to the n minus 1, or you may even just see -1 to the n. As long as the terms of the series alternate back and forth from positive to negative, it is an alternating series. Okay, so here's the test. Okay. So alternating series are of the form summation -1 to the n, -1 to the n plus 1, or -1 to the n minus 1, but everything that's left is called un. Okay, so everything that's left is called un. So now if you look at this series, you will see that you will have U1, U2 may be negative, U3 will be positive, U4 is negative, or it could start negative. U1 could be negative, U2 could be positive, U1 could be negative, U2 is positive. In any event, these series always alternate in sign. That's why they're called alternating series. Okay, so the alternating series test says this series will converge if the following 3 statements are true. Okay, so the first statement is the UN must be positive for all the n. The second statement is the UN has to be bigger than UN plus 1. In other words, the terms must be decreasing in magnitude. And then the last is the limit as n approaches infinity of the UN term has to equal 0. Okay, so this is the alternating series test. You must check 1, 2, and 3. If 1, 2, and 3 are true, then the series converges. All right. Okay, so our first example. Okay, so the first example is this series. So here, our UN is equal to 1 over n. Everything else is the -1 to the n plus 1. The only thing that left to be UN is 1 over n. Okay, so we now will check. So I will do A. I need to show that UN is positive. Well, not hard. I have 1 over n greater than 0. N is clearly positive because n is bigger than or equal to 1, which is greater than 0. So I can multiply by n and I get 1 is greater than 0, and I am quite content with that. Okay, so that checks. All right, so first off, I know UN is positive. Second, B, I need to show that UN is greater than or equal to UN plus 1, so that the terms are decreasing. So every time I find a term, it's smaller than the one before. Okay, there are two ways to show this. All right, so the first way is brute force algebra. Okay, so we can just use algebra. So in order to do that, I have UN equal to 1 over n, and that has to be bigger than 1 over n plus 1, which is UN plus 1. So I have 1 over n is greater than 1 over n plus 1. So both of them are positive, so I can multiply and get n plus 1 is bigger than n, and that just tells me 1 is greater than 0, and that's true. Okay, so that's the first way I can show it. Another way is I can use calculus. So by using calculus, I can look at the function f of n being UN. Okay, so if that's the function, how do I show, so my function f of x how do you show that a function is decreasing in calculus 1, from calculus 1? What can I do to show a function is decreasing? You remember finding intervals of increasing and decreasing in calculus 1? So for intervals of increasing and decreasing, what did I look for in order to determine when my function was increasing or decreasing? What did I do? What did I look for? Anybody remember? Okay. F of X is decreasing on intervals where F prime of X is negative. If I can show F prime of X is negative, then I know the function is decreasing, which then also means that my sequence of UN is also decreasing. So F prime of X, this is an easy one, is negative 1 over X squared, which is always negative. So that implies then that UN will be bigger than UN plus 1 because this function is always decreasing. So the next term will always be smaller than the one before. Okay, so I have shown the second part. So now that's usually the most difficult part. So let's do C. We need to show that the limit as n approaches infinity of UN is actually equal to 0. And this one is easy because this is a well-known limit. So we have the limit as n approaches infinity of 1 over n, and we already know that's a well-known limit, that's 0. So that checks. So 1, no, A, B, and C imply that the summation n equals 1 to infinity of minus 1 to the n over n converges by the alternating series test. Okay, any questions? So I have 3 things to test. The first, show that the terms are positive. Second, show that the terms are decreasing. Third, show that the limit of the UN is 0. Okay, second test. All right, so in this example, what is UN? What is UN?
Is it n squared plus 4 divided by n squared plus 5?
Thank you. Okay. So let's look at A. A says we need to show that UN is bigger than 0. And that's easy to show. All right. So we have UN equal to n squared plus 4 divided by n squared plus 5. And we need to show that's greater than 0. All right, so since n squared plus 5 is greater than 0, we can multiply both sides and get n squared plus 4 is greater than 0. And we get n squared is greater than negative 4. And that is clearly true. So A is done. Okay, B is traditionally the more difficult criteria. So this one is usually the most difficult criteria to prove. And since it's the most difficult criteria, I'm going to go on to C, only because I know that something's going to happen with C. So I need the limit as n approaches infinity of un. That is the limit as n approaches infinity of n squared plus 4 divided by n squared plus 5. So what is that limit?
Infinity over infinity.
Okay, that is infinity over infinity. So somebody,
You can take the derivative of n squared plus 4 and then n squared plus 5.
okay, and what's the derivative of n squared plus 4?
Is it, wait,
If it were
is
x
it
squared,
2n?
2n, good.
And then it's gonna be, well, 2n on the bottom as well.
Okay,
That's equal to 1.
so that's the limit as n approaches infinity of 1. That equals 1. What did my criteria say for number 3? Said my limit had to equal 0. Well, that does not equal 0. Okay. All right, so the series,
Doesn't that mean that the series fails?
yes, it fails to satisfy that criteria of the alternating series test. So we are not able to conclude that the series converges. Okay, so notice I didn't say the series diverge. I just know from this test, I can't conclude that it does converge. Okay, so the alternating series test says if all 3 are completed and satisfied, then the series converges. It does not say if one doesn't work, the series diverges. Doesn't say that. Okay, it's a one-way test. If this happens, then that happens. Okay, you can't read backwards. So if all 3 are satisfied, the series converges. That's the only conclusion I can make. So notice I don't need to go back and prove part B because I already know that part C fails. Okay. All right, one more. Okay. So here we have our third example. So what is UN?
10n divided by n squared plus 1.
Okay, so it is awesome that we can identify UN. That is the first thing we need to do. So now that we have UN, we need to check A, B, and C. So A says UN is greater than 0. So I need to show that. Okay, so that says I have 10n over n squared plus 1. Well, n squared plus 1 is positive. So I can multiply it and get 10n is greater than 0. I can divide by 10 and get n is greater than 0. And this is true since my series starts at n equals 1. Okay, so that's a true statement. Okay, so for the second statement, I think I'm going to do the derivative. I'm going to use calculus. I think it's easier. I need to show that UN is greater than UN plus 1. So I'm going to choose to show that f of x, that 4, f of n equaling UN, that f prime of n is less than 0. Actually, I'm going to make this an x. Okay, so I'm going to put the function as if it were a function of x. So I get f of x is equal to 10x divided by n squared plus 1. All righty, what is f prime of x? What is f prime of x? How do I take derivative?
Is it 2n times 10 and then plus? Am I doing it right with the quotient rule?
What is the quotient rule?
So when you find the derivative, isn't it you take the derivative of the denominator times it by the derivative of the numerator and you add it? Or am I doing something wrong?
You are doing something incorrect. Okay. Remember low d high minus high d low over low low. Bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared.
Yeah, that's what I was gonna say.
You were
Or
telling me the
there's
derivative of each of them.
oh,
You were
I'm
telling me
sorry.
2n times 10.
Oh, I'm sorry.
It's okay. Can you do it now?
So is it the whole thing?
The whole
Okay,
bottom
so n squared plus 1 then times 10x.
times the derivative of the top
Oh, 10. And then
minus the top.
yeah, and then it's gonna be times 2n.
I got n's and x's in here, making
Well,
myself crazy.
2x.
Okay, thank you.
And then it's gonna be divisible by x squared plus 1 squared.
That's right. Okay. When you simplify this, you get negative 10x squared plus 10 divided by x squared plus 1 squared. I'm going to factor out the negative 10. You get x squared minus 1 divided by x squared plus 1 squared. And that is truly less than 0 if x is bigger than 1. So that means un is bigger than un plus 1 for n bigger than 1. And we're okay with that. That checks. C, show the limit as n approaches infinity of un is 0. Limit n approaches infinity of 10n divided by n squared plus 1. What is that limit?
Infinity over infinity.
Okay.
So it's it would be 10 and then over 2n.
10 over 2n. Good. What's that limit?
Isn't it 0?
Mm-hmm.
Because it's the bottom is getting bigger.
Mm-hmm. And goes to infinity in the denominator. Okay. I think we've shown all three. So by A, B, and C, the summation n equals 1 to infinity of 10n divided by n squared plus 1 converges by the alternating series test. Any questions? Okay, that was test number 8. All right, next we have the test for absolute convergence, which is test number 9. Okay. This test, a series summation an actually converges absolutely. Okay, so that's the new term. This converges absolutely. If the corresponding series of absolute values converges. That is, if the summation an converges, then the summation of an converges absolutely. If the summation of an, the absolute values converges, then the original series converges absolutely. Okay, any questions about that definition? I'm going to take my original series, and that's the one I'm checking. I'm going to take absolute values of those terms. If that series converges, then the original series converges absolutely. So we have some examples. Okay, first example is this. Now, this is an alternating series, which means I would use the alternating series test. If I use the alternating series test, it will show that this series, okay, so it's actually easy to see that this series is going to converge. One, UN, what's UN? What is UN?
Is it, wait, is it, 1/n², or is it just?
That's it. So that's UN. All the terms are positive. UN plus 1 is bigger than UN. I'm sorry, UN is bigger than UN plus 1. And the limit of that is 0. So yes, we can show that this series converges. All right, so the question is, does the series converge absolutely? So now we need to use the test for absolute convergence. So in order to do this, we now need to examine the summation n equals 1 to infinity of the absolute value of the AM terms. And that for us would be the summation n equals 1 to infinity of the absolute value of -1 to the n over n². So that is the sum n equals 1 to infinity of just 1 over n². Okay. Wow. What is that series? What is that? It's a special type of series.
Is it the geometric?
P series.
No,
That's P series.
I was wrong.
Rodney, what made you think it was a geometric series?
I was probably contradicting myself because last time I said it was P series and I was wrong and it was geometric. So I got it mixed up again.
Okay, that's all right. We're gonna get it straight. Okay, this is indeed a P series. Remember, our P series will look like the summation n equals 1 to infinity of 1 over n to the P. P series have a form. They all look the same. Nothing changes in the P series. They all look the same. So therefore, this is a P series. What is N? I'm sorry, for P. What is P? P is equal to what?
2.
2. And when does this series converge or diverge?
When it's less than 1.
Okay,
I think when P equals 1, it diverges.
okay,
So
when P
when it's
equals
not
1, it
equal
does
1,
diverge.
so when it's not 1, then it converges.
Okay, we're getting close. So I got a little bit from each of you. This actually only converges when P is greater than 1.
So it converges when P is greater than 1, but diverges when P is less than or equal to 1, right?
Exactly.
Okay.
Okay. So this series converges. Right? So if that series converges, that implies this series converges. Okay. So then that implies this series with the negative term converges absolutely. So notice when this one right here does not have the absolute value. That's the original series. We showed the one with the absolute value converged. Then that shows that the one without the absolute value converges absolutely. Okay. I thought of this example, so I'm going to throw this in here in the list of my notes, just throwing it in. Let's look at the summation n equals 1 to infinity of the sine of n over n to the fourth. Now this is what we call a hidden alternating series. It's hidden because, you know, sine goes positive, goes up and down from 1 to -1 to 1 to -1. So the signs do change, but it's not quite an alternating series. But I still can use the test of absolute convergence. So this is not an alternating series in true form. It's not a true form alternating series. But I can use, I should say we, not just me, all of us. We can use the test of absolute convergence. Okay, so how can we use it? Well, the reason why we can use the test of absolute convergence is because I'm going to take the sum n equals 1 to infinity of the sine of n over n. That's my original series. N to the fourth is my original series. So now we're going to look at the sum n equals 1 to infinity of this absolute value of this. So the absolute value is the sine of n over n to the fourth. But that's just the sum n equals 1 to infinity of the absolute value of the sine of n over n to the fourth. Now the sign goes between 1 and -1. So I know this is less than or equal to the sum of 1 over n to the fourth. Okay, so we got a lot going on. We're trying to determine whether this series converges. we're going to look at this series, which is in absolute value. And so we were able to show that the absolute value of the series is less than this series. Okay. So here's my question. What do you know about this series? What do you know about that series? It has a form. It has information. I can get it directly. What's the form?
It's the P series.
It's the P series. What's the information it's giving me?
N to the fourth.
Right. So what is P?
4.
P is 4. So does it converge or diverge?
It converges.
Awesome. Okay, so this last series is a P series. Okay, so we got all that information. Okay, it's a P series. P is equal to 4, which is greater than 1, so the series converges. Okay, now here's the trick. What am I using here? This series is less than that series. So what am I using? I have one series less than the series that already converges. What am I using? Which test?
Is it the alternating? The alternating series test.
What'd you say?
Is it the alternating series test?
Okay, so we used the alternating series test in the very beginning just to show that the series, we didn't use the alternating series test on this. Okay, we couldn't use the alternating series test on this because this was not a true form alternating series. So we didn't use the alternating series. We're using the test of absolute convergence. So now I'm picking your brain. Remember from previous tests, when you had a series and you could make it less than a series that converged, or you can make it greater than a series that diverged. What am I doing when I have those two types of tests? Two types of series. What am I doing? I have one less than the other. What am I doing?
Direct comparison.
I'm comparing them. Okay, good. I'm comparing them. Now, am I using a limit? No. When I say direct comparison, that is directly saying I am shorter than somebody who is 6 feet tall. Okay, so a direct comparison just literally directly compares the two things. Okay, so this test, I have this series I know is less than a series that's convergent. So by the direct comparison test, this second series converges. So I know here, this converges. By the direct comparison test. It is strictly less than a series that converges. So by the direct comparison test, it converges. So now, so we have this. So we have the summation n equals 1 to infinity of 1 over n to the 4th converges, which implies the summation n equals 1 to infinity of the absolute value of the sine of n over n to the 4th converges by the direct comparison test. And then the summation n equals 1 to infinity of the absolute value of the sine of n over n which is the same as the sum n equals 1 to infinity of the absolute value of of the absolute value of the sine of n over n to the fourth. This converges. Oh, no. And that implies the summation n equals 1 to infinity of the sine of n over n to the fourth converges by the absolute test of convergence. So in other words, I look to see if the absolute value converge. And then when I look to see if that converged, I was able to show its absolute value is less than something that converged. So I used a direct comparison test to show the absolute value converged. Once the absolute value converged, then the other series converges absolutely. Okay, any questions? Again, I'm posting the notes. It takes a little bit of time to absorb some of the concepts, but if you take it piece by piece, you get it. Okay.
Did we take attendance yet?
I did. Who is that?
Benaya Gillis.
Oh, hi, Benaya. Yeah, you're marked absent. I'll fix that.
Okay, thank you.
You're welcome. Okay, so now let's look at this test. Did I do this one? I did not. This is number 2. Okay. Okay, so we can use alternating series test, and we will show that this series converges. Okay, so by the alternating series test, this will actually converge. But let's try the test for absolute convergence. Okay, so the test for absolute convergence says what? Let's examine the summation n equals 1 to n, I'm sorry, n equals 1 to infinity of the absolute value of this. Well, that is just the sum n equals 1 to infinity of 1 over n. So the absolute value of our terms looks like just this series. What series is this? That is a well-known series. What series is it?
Is that one geometric?
Why do you think it's geometric?
Because that looked like the other one that was geometric. I was just taking a good guess.
Okay, so I think you know what you're saying, but I think you're just saying the wrong test. It does look like another one that we just did. It looks like this one.
Oh, it's the P series.
Okay. I knew you knew what you were talking about. You were just saying
Yeah.
the wrong thing. Okay, so now the P series when n equals 1, you are right. That is a P series. The P series when n equals 1 has a special name. This series has a special name. This is the harmonic series. You remember? And the harmonic series, does it converge or diverge? This is P is equal to 1. Antoine, it's on the tip of your tongue.
You said when P equals 1, the series, it should diverge, right?
Good, this diverges. Told you you had it, I could tell. Okay, so now, what does that test for absolute convergence say? The test for absolute convergence says, if the summation of this AN converges, then the summation of the regular series converges absolutely. Okay, so the only thing we can say here is by the test for absolute convergence, this series does not converge absolutely. Okay, but it does do something. And we'll find out what it does on Thursday. Okay, I'm going to post these notes, but there's one other part of this section that is not included yet. So you'll have to get the whole part of the notes together. All right, so that's the end of the lecture. Any questions?
I had a question.